Hey everybody, this is Larry. This is day one of the December Leetcode Daily Challenge. Hit the like button, hit the subscribe, and join me on Discord. Let me know what you think about today's farm. If you're new to this channel, especially for the December challenge, usually I go over my thought process and everything is recorded live, including me thinking about the explanation as I'm going to you. So if I don't go directly to the explanation, feel free to watch this on 1.5x or 2x or something like that. But yeah, or just skip forward to near the end, right? So today's problem is maximum depth of binary tree. Given root of a binary tree, return its maximum depth. Okay, so the depth is just the longest path from the root to the leaf node. This is a standard definition, and this is a standard, tree traversal problem. You could solve it with binary. You could solve it with breadth first search or depth first search. For me, I generally like to solve it as depth first search. So let's get right to it. So recursively, you can define the definition of depth is just you go to the definition of the depth is you go to the root the the depth of the root is you go to the depth of its children plus 1, right? So given that recursive definition, we can easily just go through it. So definitely, and I would say this is kind of a little bit on the easy side, but that's only because many people have practiced this a lot. These kind of tree problems come up on interviews all the time because, well, there's a very obvious inherent recursive structure. So definitely recommend practicing this if you're struggling. But yeah, so this is what I'm going to do. And honestly, if this was on a contest or something like this, I'll probably do it in about 2 minutes. So yeah, so let's just say we have a depth function. So if node is none, we return 0. Actually, double check real quick. Because sometimes some people define depth as the number of edges from the root to the bottom. Sometimes some people define it as the number of nodes. So I just wanted to make sure for this problem, and it seems like it is the number of nodes. Okay, so then we could do this. Else we can just do the depth is equal to so yeah, I'm gonna write, usually I write it more tersely, but I'm gonna write it out just for easier to understand code. So yeah, the left depth is equal to depth of node dot left plus 1. Right depth is equal to the same thing, but to the right side, obviously. And then now actually, and then now we return to the max of left depth, right depth plus 1, right? And then now we can just return the depth of the root. And it seems like we didn't need a helper function, to be honest, but that's the way that I always think about it. Because sometimes there are a lot, you need to do something to keep track of state or something like that. So that's why I always do this. But actually, you could have used the input function that they gave you, but I don't think that shouldn't matter that much. But as I am recording this live, you could pretend that there's a montage music right now as I put in the different test cases. So we should always test our stuff. Looks good. Let's submit. And cool. So what is the complexity of this algorithm? Well, we look at each node in the tree once, because you have to look at every node in the tree. So it's going to be O of n in terms of time. In terms of space, there's no explicit space allocation, but we do use the stack space as we use recursion, and the max depth is just going to be the max depth of the tree. So it's going to be the height of the tree, which is O of h. And yeah, so this is going to be O of h instead of space, and h can of course be, in the worst case, be n, we have like a linked list type thing. So this is linear time, linear space, and that's all I have for this problem. Let me know what you think. Hit the like button, the subscribe button, join me on Discord again. I am going to do this every day for December. So feel free to come back, hit the subscribe button, and we'll do this together. I will see you tomorrow. Bye bye.